This video will cover sections 10.2 and 10.3, which is talking about parametric equations in calculus. So first of all, we're going to review parametric equations that you learned in pre-cal. So just to kind of let you know, remind you what parametric equations represent. So consider the path of an object along the curve, the quadratic curve there. This equation would relate the height of an object with respect to time. So that means the x-axis is time when we're looking at the regular rectangular coordinates, and then the y-axis would represent the height of the object. Now, with this function, at any given time, you can find how high the object is, but you don't know the horizontal distance. You don't know how far horizontally the object has traveled. So what parametric equations allow you to do is to introduce the parameter of time. So then you would create a parametric equation where you have both an x component and a y component, and you can figure out how far horizontally and how far vertically the object has traveled. Now, this equation, I'm not going to work with this one because this one actually didn't work out. So I'm going to kind of skip this first question. Just know that in order to do that, you need to introduce what we call a parameter, that third variable. All right, so what we're going to do is, like I said, we're going to skip that problem. We're going to look at this next part here. And we're going to actually, again, this is not calculus. This is something you should have learned in pre-cal, so this is hopefully a review for you. But I'm going to give you a set of parametric equations, and we're going to plot the points. Now, when you have parametric equations, you have something called an orientation. So a lot of times we think of that t as if it were time. It's not necessarily time, but it kind of helps to think of it that way. So at given times along the graph, you can see kind of where my function would start and how it moves along the curve. So if I were to ask you to draw a parametric equation, and you did so without showing the orientation, which looks like arrows on the curves, then you would actually not be correct. You would get points deducted for that. So to sketch a parametric equation, what you need is you need to have like a t-chart, but with three columns. So we have our independent variable, which is our t, and then we have two dependent variables, both x and y component. So our t, for this first example, they said they want t to be between -1 and 4. So we're just going to use the integers from -1 to 4 to evaluate what's going on here. And so now you just plug in t into my x equation and my y equation. So I'm just going to quickly do that. So when I plug in -1 into t squared minus 2t, you get 3. Plug in 0 is 0, and so on and so forth. All right, when we plug in our t values for y, that's much easier. It's just t plus 1. So we have 0, 1, 2, 3, 4, 5. Okay, so now when we graph this, we want to look at kind of how far x and y go. So x goes from -1 here to 8. So I'm going to make sure that my x-axis would go from -1 to 8. And then my y value goes from 0 to 5. So I'll make sure that's reflected. Okay. So let's say -1, 8, and 0, 1, 2. All right. Okay, so just kind of a rough sketch there. All right, so now what I'm going to do is I'm going to be plugging in or plotting these points. So my first point is the point 3, 0. Okay, so at that point, that's when, not t equals 0, sorry, t equals -1 there. Okay, and then I'm going to move to the next point, which is 0, 1. So I'm going to be moving from the point 3, 0 to that point 0, 1. So we have this orientation, this time component going on here. All right, then -1, 2, then 0, 3, then 3, 4, and then finally 8, 5. So actually what you're going to end up getting is kind of this sideways parabola. Now you don't want to continue on this graph like we do with regular functions. You don't want to go beyond that time restriction from -1 to 4. You can label as you go along, but you don't have to. But you do need to see arrows showing the direction that it's going. And then here's my ending point, which is t of 4. All right, so that is the parametric equation for this example. All right, so now it says to write the corresponding rectangular equation by eliminating the parameters. So what that means is you kind of want to just fuse these two components together. and you would come up with an equation that represents that in rectangular function. The easiest way to do that is your y value is t plus 1. So we want to get t by itself. So if we solve for t for that equation, we would get y minus 1. And then we would just substitute that into our x equation. So that would be x equals, our t is y minus 1 squared minus 2 times y minus 1. Again, I'm looking at that function for x. Now, you don't have to simplify that, so I'm going to leave it alone, but you can see that you have x as a function of y squared, so this is a sideways parabola, which is what we have. Now, one thing you do have to remember is if I were to graph this equation right here, this x equals y squared function, you would have the full function. So you have to restrict the domain or range here. So our y value, since this is a function of y, we want to restrict our y value. So just like t was restricted from -1 to 4, looking at our function, our y values, the smallest y value goes from 0 all the way up to 5. So you do need to state that when you write it as a rectangular equation, or it would be wrong. Okay, so that's a review. So now we're going to jump into how does calculus work with parametric equations. All right, so we have a curve. So anytime we have like a function, we call that a curve. So this was our curve for that parametric equation. So we call a curve that's represented by that x component and y component here, two different functions. We call that curve is smooth if f prime and g prime are continuous on the interval and not simultaneously 0. So basically, it's a continuous smooth curve without any breaks, okay? So for the parametric equation to be continuous and smooth, both their derivatives of the components need to be continuous, except possibly at the endpoints of that interval, okay? So like I said, essentially no sharp turns or points or holes or anything like that. All right, so if you have a smooth curve, or think continuous curve, is given by, and actually differentiable, is given by the parametric equations x and y. Then how do you find the slope of a parametric equation? Well, slope of a rectangular equation is dy over dx. So that is the same thing that we're going to be finding for the parametrics. We're finding dy dx. Now, remember my y component and my x component are both in terms of t. So if I were to take the derivative of, let's say, our f with respect to t or g with respect to t, you're taking the derivative with respect to t, not with respect to x, not with respect to y. So dy dx would be the ratio of dy dt, that derivative with respect to t, over dx dt. And you can see that those dt's are going to cancel out. And also, given that dx dt does not equal 0, therefore you would have undefined. Okay, so let's try this. So if we want to find this dy dx for the curve given by x equaling sine of t and y equal cosine of t. So we want dy dx. So remember, dy dx is just as simply dy dt over dx dt. It's that simple. Because, like I said, the dt's would just cancel out, leaving you with dy dx. So we need to find the derivative of both our x component and our y component with respect to t. So the derivative of our x component with respect to t is cosine of t. The derivative of y with respect to t would be negative sine of t. So now we have dy dt, negative sine, over dx dt, which is cosine. And when we simplify that, we get the negative tangent of t. Okay, so pretty straightforward there for the parametric equations. Now, the first derivative of a parametric equation is pretty straightforward. However, the higher order derivatives, second derivative, third derivative, get a little bit more complicated. Now, don't be scared by what you see here. It looks more complicated than it really is. So if you were now to find the second derivative, you're taking the second derivative with respect to x, but my equation is in terms of t, okay? And you have both this x component and y component. So what you see here is we broke down the second derivative of y with respect to x. So what you can do is you can break that down. You're taking the derivative with respect to x of dy dx, but dy dx is in terms of t. So what you want to do is you're going to take the derivative with respect to t of dy dx, since it's in terms of t, and then to counteract for that, to kind of make up, and you can kind of see how this works algebraically. So you take the derivative of that derivative, dy dx, And then you divide by dx dt, and that takes care of that taking with respect to t or x piece. Okay, so let's see how this works. So all you have to remember is to take a higher order derivative of the parametric. Is just take the derivative of dy dx. So I want to take the derivative with respect to t of my dy dx that I found to be tangent of t. And then you just simply divide by dx dt. And that dx dt piece is exactly what we found from previous. So our dx dt was just cosine of t. All right, so again, it's not that bad. So the derivative of negative tangent. Derivative of tangent is secant squared. So this would just be negative secant squared, again with respect to t. And then divided by dx dt, which we found in the first problem to be just cosine. Okay? So then you can clean that up if you want to. So that would be 1 over cosine of secant. So that would be negative secant cubed of t. Okay? All right, so now let's try the third derivative. Now, good news is every higher order derivative is the same process. You take the derivative of the previous derivative and divide by dx dt. Okay? So let's take the derivative of, with respect to t, of the previous derivative, which was negative secant cubed of t, and then you're going to divide by dx dt. Now, the derivative of secant is secant tangent, but this is chain rule, so you're first going to bring down the negative 3 of secant squared times the derivative of secant, which is secant tangent, divided by dx dt, which is cosine. Now, you could do a bunch of algebra there and simplify that, but that's not what we're concerned about today. Okay? So again, all you have to do is when you take derivatives of parametric, take the derivative of y, dy dx, and then divide by dx dt. Okay? All right, so now next question. For the curve given by x being root t and y being 1/4 times t squared minus 4, where t is greater than 0, find the slope and the concavity at the point 2, 3. Okay? So define the slope. To find the slope, we want dy dx at the point 2, 3. So to find dy dx, we just simply find dy dt over dx dt. All right, so dy dt, that would be the derivative of 1/4 times t squared minus 4. So the derivative of that is 1/4 times 2t divided by dx dt. That would be 1/2 t to the negative 1/2. If we clean that up a little bit, we would get t over 2 over 1 over 2 square root of t. And then when we simplify that, we get t, the 2's cancel out. So then that's t times the square root of t, which is t to the 3/2. Okay? So that's dy dx, but they want to find the slope at the point 2, 3. So I want to calculate dy dx, so this is dy dx up here. And remember the notation with dy dx, you have this big like such that you're at the point 2, 3. Now, here's the problem. Our dy dx is in terms of t, and I want to find it at the point 2, 3. That's x and y. So how do you find t if you know x and y? Well, you use either of your parameters, x or y. X is easier to deal with. So I'm going to plug 2 in for x. So 2, let's use a different color. So 2 is equal to the square root of t. So when x is 2, that means that t is equal to 4. Okay, and you could see that that would work out also with the y value. Okay, so when I actually notate this, instead of saying such that at the point 2, 3, I want to say such that at the time t equals 4, because my derivative is in terms of t. All right, so now we say that that is 4 to the 3/2, which the square root of 4 is 2, 2 cubed is 8. So the slope at the point 2, 3 is 8. All right, so similarly, we're going to do the same thing with the concavity. So now we need to find the second derivative. So our first derivative was t to the 3/2. So our second derivative, we're taking the derivative of a parametric. So that means we're going to take the derivative of dy dx, which is 3/2 times t to the 1/2, divided by dx dt. And so dx dt we found previously is 1/2 t to the negative 1/2. When you simplify that, you're going to end up with 3t. Okay? So now we want to determine the concavity at the point 23, which we already found was at the time 4. So this would be 3 times 4, which is 12, which is greater than 0. Therefore, our function, or our curve, is concave up at t equals 4. Okay? All right, so like I said, pretty straightforward, just a little bit different, but pretty basic when it comes to the calculus. All right, so we've talked about finding slope and concavity. Now we're going to talk about finding the equation of a tangent line. So in number 4, it says find the equation of a tangent line to the curve at a specific value of the parameter. So again, we have our x and y components, and then we want to find that equation of the tangent line at t equals 1. All right, so again, we want dy dx, because to find the equation of a tangent line, we need to find the slope at that point. So dy dx is just dy dt over dx dt. Now dy dt, y, 1 over t plus 1, that's t to the negative 1, so then that would be negative t to the negative 2 would be the derivative of that, divided by dx dt is just 1. So in other words, this is negative 1 over t squared. All right, and then I need to evaluate that at rt equals 1. They give us the t in this problem. So dy dt when t equals 1 is just equal to negative 1. So that's my slope. Now, to write the equation of the tangent line, remember you need an x and a y and a slope. I actually only have my slope right now. I do not have the point. So this is kind of the opposite of what we did in the last problem, where I need to calculate the point. But all you have to do, you have your t equals 1, so you just plug in 1 for t in both equations. So my x value is 0, and then my y value would be 2. So now you take your point and you plug in the point slope form. So y minus the y value equals the slope times x minus the x value. No need to simplify, that's my answer. Okay? All right, so just kind of some things to keep in mind. When you have the parametric curves, remember you have the x component and the y component. So when you find dy dx, you have dy dt over dx dt. So therefore, a parametric curve will have a horizontal tangent, a slope of 0, whenever dy dt equals 0. And then it would have a vertical tangent whenever dx dt equals 0. And I should also make a note here that you'll have a horizontal tangent whenever dy dt equals 0, and also dx dt does not equal 0, because if they were simultaneously 0, then that would be indeterminate. We have a problem there. Okay, and so also for vertical tangent, we also have to make note that dy dt could not equal 0 at that point. All right, so we've talked about derivatives, concavity, tangent lines. Now we have one more thing to talk about with parametric, and that is arc length. Okay, we've learned arc length before. I know it's been a while. You probably you don't remember that off the top of your head, but this is something that you will see with parametric form. This is something that you will need to memorize. And this is a good review of the other arc length. Okay, so the arc length before in rectangular format. So in rectangular, arc length we denote arc length by an s, is the integral from a to b of the square root of 1 plus the derivative of our function squared. Okay, so that is rectangular arc length. If you don't have that memorized, you need to memorize that. So that's with the one function. So now if we have the two functions, it's very similar. It's just instead of 1 plus the function squared, we have both derivatives of both components, and we just square them. So we have dx dt squared plus dy dt squared instead of the 1. Okay, so that's something that you need to memorize. So now let's get practice with that. So for number 5, we're going to find the arc length of the curve on the interval. So first of all, I have x and y. I need to find dx dt and dy dt. Not dy dx. I don't need to bring it actually together for arc length, but I do need to find them separately. So I'm going to go ahead and find dx dt and dy dt. So X is a quotient, but you don't have to use the quotient rule because you're dividing by a constant. So the derivative would be 3/2 times 8t plus 8 to the 1/2 power, and then don't forget times 8 by chain rule. And then the dividing by 12, you're just going to stay dividing by 12. And so actually what's going to happen is all those constants, 3/2 times 8 divided by 12, is they're actually all going to cancel out, and you're going to be left with just the square root of 8t plus 8. Okay? Then dy dt is easier. It's just 2t plus 1. All right, so now to find the arc length formula, again, we use s to denote the arc length. We're going to take the integral from our values for the limits do need to be t values, and they are. So t is from 0 to 2 of the square root of dx dt squared, which, yes, I am going to write it out just so you can see it in your notes, but obviously the square root of 8t plus 8 squared will just be 8t plus 8, plus 2t plus 1 dt. Okay, now you would continue on with that to find the arc length, but I'm not going to do that just for sake of time. This is pretty simple to integrate. You'll end up getting this 8t plus 8 plus 2t plus 1 squared. And so what's going to actually happen is this will be something that you can integrate by hand. So when you distribute all of that out, you're going to end up getting 4t squared plus 12t plus 9, which is a perfect square. So that becomes 2t plus 3 squared. So I know I'm going really fast here, but I just wanted to show you that you might be expected to do something like this by hand, and I'm just showing you kind of steps that you would take in order to get it down to something that you can integrate. Okay, so if this was a calculator problem, you could just put that in the calculator, or they might just ask you to write an expression of the integral, but sometimes you will have to carry it all out by hand, so I just wanted to show the steps there. Especially, I mean, it's good review because we haven't done it in so long. So then the integral of 2t is t squared plus 3t, evaluate from 0 to 2, and you end up getting 10 as your arc. Okay, so that's really it with parametric form. This, like I said, it's not too bad. It's just a few things that you need to be familiar with. Now, there is a second video that I'm going to do, and I want you to watch in correlation to this, and that's on vectors. So that's parametric.